This project presents the design of a quarter-scale tractor produced during the fall semester of 2016. The tractor was designed to compete in the 2017 American Society of Agricultural Engineers quarter-scale tractor student design competition, which is on June 1st through 4th in Peoria, Illinois. The tractor will be constructed and tested during the spring semester of 2017. The competition consists of written and oral presentations of the tractor design in front of industry representatives, as well as test courses for the tractor. These tractor performance tests include a maneuverability and durability course, as well as 3 tractor poles with different ballast weights. The goal of the design is to produce a tractor that will be competitive in each performance event, as well as incorporating design features that will make it attractive to manufacturers as a potential new product.
The competition supplies each team with a 31 horsepower Briggs & Stratton V-twin engine and a set of Titan 26 by 12 by 12 tires that are to be used as the drive tires in the design. The resulting tractor design has a 70-inch wheelbase and is 48 inches wide. The overall length is 85 inches, including a ballast rack ahead of the front axle and a hitch and wheelie bar behind the rear axle. The weight of the tractor is approximately 750 pounds, providing some buffer for staying under the maximum of 800 pounds allowed by the competition. The center of mass is located so that the front wheels will not leave the ground until the maximum expected pull of 5,000 pounds is achieved.
So then we designed a hitch in order to pull the weight of the sled. We made it so it was completely vertically adjustable. So this will allow us to change the height in between different events of the competition. The hitch itself had to be bolted to the frame, so we incorporated that as well, and it will withstand the weight of the sled as we pull it during all 3 events. We also designed a wheelie bar and bumper bar system. So this is the farthest most point of the tractor. We put bumper bars that reach further than the wheels. The wheelie bar itself is to allow the tractor to stop moving vertically if it does in fact do a wheelie. And then the bumper bars are set so that if the tractor stops and the sled keeps going, that impact will not destroy the tractor itself, but instead just hit those bumper bars. And so both of these had to be combined into one system, as you can see, and then the bumper bars had to be a little bit farther out than the wheelie bars, and then the entire thing is attached to the end of that frame.
For our transmissions, we're using Parker HTJ series hydraulic transmissions. They're actually hydromechanical variable transmissions. These are very small, compact units. They're very lightweight, but can produce large amounts of torque with relatively small inputs. And we had to do something fairly interesting. We're having them 90 degrees out of their normal working plane. We worked closely with Parker to determine if this was possible, which we finally decided it was.
For our front axle and steering system, we chose to buy rather than build most of it. We're going to source it from a John Deere 318 tractor. They're about the same size. They have the exact same size rear and front tires that we were planning to use. They're about the same weight. These are 750-pound machines. What it looks like is it has a pivoting design, which is going to help us reduce torsional frame stress and improve ride quality through the durability course primarily. The durability course is going to involve rolling over curbs in loose sand, and each front tire has to move independent of the chassis to allow it to just smoothly roll over everything. We went with a wider turf style front tire to keep flotation in the 6 inches of sand in the durability course. That's going to prevent us from getting stuck.
There are 3 main things that are going to restrict how much a tractor can pull. They are the stability of the tractor. So basically, as the tractor pulls, there's going to be a moment generated between the rear tire and the ground that'll tend to lift the front tires off the ground. When this happens, we'll lose stability and lose the ability to steer. The second thing is losing traction between the rear tires and the ground. This would happen if the coefficient of friction between the rear tires and the ground is too low and the rear tires spin without grabbing. The third restriction is power restriction. That is when our engine simply cannot turn the rear tires anymore because of the load that they're under. Our design is seeking to maximize the amount of energy that our engine has, so we would like our tractor to be limited by the power and not by the other two variables. In order to do this, we want to get our center of mass located appropriately by changing where our ballast placement is and where the placement of the other heavy objects and parts of the tractor are. The desire is to get our center of mass approximately 30 inches in front of our rear axle, and this will allow us to keep the front axle on the ground entirely through the pull, and it should allow us to maximize the pull and pull somewhere in the neighborhood of 2,500 pounds.
This concludes the critical design review of Montana State University's quarter-scale tractor. The design team is composed of Shay Steinbeiser, Levi Rosler, Shelley Dorkin, Jonathan Dupé, Jacob Lear, and Cody Paceman. Thank you for watching.